Good day, everyone. Welcome to our session for today. So, this is our second to the last topic of our course, Math 111. So, finding roots of equations using Newton's method. So, our objective for this lecture is at the end of the period, you should be able to determine the roots of an equation using Newton-Raphson method. Actually, class, there are a lot of methods in finding or determining the roots of an equation. But we'll focus our discussion on the Newton's or Newton-Raphson method. So these are the different methods. You have the bisection method, Newton or Newton-Raphson method. We have the second method, fixed point iteration method, false position method, and Euler's method. So you will learn all this in your numerical methods subject or course in the future. So first, let's talk about root or roots of equations. A root or solution of equation f of x equal to 0 are values of x for which the equation holds true, meaning all the values of x in the function of x that can make both sides equal, both sides of the equation equal. Okay, so that's what we call the root or solution of equation. Methods for finding roots of equation are basic numerical methods, and the subject is generally covered in books on numerical methods or numerical analysis. Numerical methods for finding roots of equation can often be easily programmed and can also be found in general numerical libraries. So make sure that when you are reading or looking for references, so you have to make sure that you aren't confused by the terminology. So below are just the same. When you see this solving a polynomial equation, f x equal to 0. So this is just the same as finding roots of polynomial equation p sub x equal to 0. And it is also the same as finding zeros of a polynomial function p of x, or factoring a polynomial function p of x. So these are just the same thing. So don't be confused by this terminology. So if you read any of this, so they mean the same thing. Okay, so you have to take note of this. So Newton's method in numerical analysis, Newton's method, also known as the Newton-Raphson method, named after Isaac Newton and Joseph Rapson, is perhaps the best known method for finding successively better approximations to the zeros or roots of a real valued function. Newton's method can often converge remarkably quickly, especially if the iteration begins sufficiently near the desired roots. So just how near sufficiently near needs to be, and just how quickly, remarkably quickly, can be. That depends on the problem. So given a function f of x and its derivative f prime of x, we begin with a first guess. So our first guess can be labeled as x sub 0. So our x sub I means initial guess, or we can use x sub 0. So provided the function is reasonably well behaved, a better approximation x sub 1 is given by this equation. X sub 1 equal to x sub 0, where our initial guess or initial value is labeled as or denoted as x sub 0, minus f sub x sub 0 divided by f prime of x sub 0. So our x sub 1 can be solved using our initial guess. then subtract by the ratio of the value of the function with that Gibbs number or Gibbs number and the value of the first derivative using that Gibbs number. So meaning you have a function, then you substitute that value, whatever is this value, to that function and divide that result by substituting this Gibbs value to the first derivative, and you will get the value of the first derivative, and you can solve the value for x1, x sub 1. Right, so the process is repeated until a sufficiently accurate value is reached. Then we have this in general, the Newton's method, the Newton-Raphson method is given by this equation: x sub n plus 1 equal to x sub n minus f sub x sub n divided by f prime of x sub n. Alright, so you have to remember this formula, class. So this one, this is our initial Gibbs of the root, and this one is the next Gibbs of our root, which is not the real root, but not the true root, but an approximate root to the given function. An illustration of one iteration of Newton's method, the function f is shown in blue and the tangent line is in red. Okay, so this is just an illustration of one iteration. So you are given the function. This is blue color. Okay, so this is the function, and then we approximated this function by its tangent line. Okay, so initially we let this be this is our initial Gibbs of the root, where the true root is here, is found here. And we have here the tangent line, tangent at this point. Okay, so this tangent line crosses the x-axis at this point, and this will be our second approximate. We call it as x sub n plus 1. Okay, so surely this one is better than this first Gibbs. Okay, so this approximate value of the true root or true solution, this is much better than this, because this is much closer to the true root. The true root is found here. Okay, so we see that x sub n plus 1 is a better approximation, as I mentioned a while ago, for the root of x of the function f. The idea of the method is as follows. One starts with an initial Gibbs, or u starts with an initial Gibbs which is reasonably close to the true root. Then the function is approximated by its tangent line. Okay, approximated by its tangent line. Right, so this is the tangent line. So this function is approximated by its tangent line. So this is the true root, this is the approximate root. This is the initial Gibbs of the root. Okay, and one computes the x-intercept of the tangent line. So what is this x-intercept? So the x-intercept means that is the value of x, the value of x at the point where the tangent line crosses the x-axis. So what is the value of x at this point? Meaning the abscissa at this point, the intersection of the tangent line and also the x-axis. So this is our x-axis. This x-intercept will typically be a better approximation to the function's root than the original Gibbs. Okay, if the original Gibbs is x sub n, so this is a better approximation, x sub n plus 1. And the method can be iterated. The method can be iterated, or can be done again and again. Right? So we have here the derivation. So Just copy the previous slide's graph. So this is the graph of the function, and this is the graph of its tangent line. Okay, and then we label this point here as point A, and we label this point of tangency, the intersection between the tangent line and the graph at point B, and this point where the tangent line crosses the x-axis, we call it point C. And we let the angle between this x-axis and the tangent line, this tangent line, we call this as alpha. Then we will use this right triangle, okay, to find the slope, where the slope is the first derivative of our function. So from our trigonometry, we have the sukatwa. Remember the sukatwa in your trigonometry. So in a right triangle, we have what we call su. We have the su. So this is a very important concept class, no, from our trigonometry. So if you can still remember this, in a right triangle, we can use this code, no, sukatwa. So in this case, we will use tangent. No, we have to make use of this height of the function, and also this increment, because this will change. No, this will change as you vary the position of the tangent line. So in this position, we have this. Okay, this is our alpha. No, this is our angle alpha. I will rewrite it here. So this is our alpha. So tangent of alpha. So from the definition, tua. T means tangent. So O means opposite over adjacent. So this is the opposite. So opposite of this length, it is AB. AB. Then divided by adjacent AC. So tangent alpha is equal to AB over AC. Okay. Then we know that the slope of the tangent line is just the derivative, the first derivative of this function. All right, so we have f prime of x of I. So at this point, we have x of I. Okay, so we use this f x of I equal to f of x of I divided by x of I minus x of I plus 1. Okay, so where is this coming from? So this is coming from this f of x of I. This is the height of the function at this point. Okay, so this is the height f of I, f of x of I. And then x sub I minus x sub I plus 1. So this x sub I class is just the distance, the distance from the y-axis, distance from the y-axis towards point A. So this is our x sub I. And then our x sub I plus 1. So this is the distance from this point C, from the y-axis. So this is our x sub I plus 1. Okay, so from here, we can calculate the difference. So the difference is this. Okay, so the difference is this one, class. So this difference is this one is, this is our x sub I, this is our x sub I minus x sub I plus 1. Okay, and if you manipulate this, you can rearrange this. You can rearrange this one, class, and you can solve for x sub 1. So to solve for x sub I plus 1, So to solve this x sub I plus 1 like this, you just multiply both sides by this. Okay, multiply both sides by this and divide both sides by this. So this will, it's just like cross multiplication class. So this term here will be on the left side of the equation, and this one will be the denominator of this. Okay, so you have now a ratio of f of x sub 1, which is this one, divided by f prime of, sorry, x sub I, f sub x sub I, okay, divided by this f prime of x sub I. Then why negative? Why negative? Because you have to, when you cross multiply it here, so what will happen is that this is negative. We want to solve this. So to becomes positive, you have to multiply both sides by negative 1. Or you can uh, better, no? Multiply both sides by negative 1. So this becomes positive. Okay? And this becomes, or you just, what happens is, this becomes positive because when you multiply both sides by negative, so this becomes negative, this becomes positive. Okay, so this becomes positive, and the ratio here, originally this is positive, so this becomes negative. Okay, and then you transpose this is negative initially. When you transpose that to the other side, so this becomes positive. So originally this one class is because this part here, so when you cross multiply this one, so it will be on this side, right? So this will be x sub I minus x sub I plus 1. Okay, then equal to, so this will be, you cross multiply this one there, okay, and this one, so it's just like they're interchanging place. So our numerator will be this one, f sub x sub I, okay, divided by f prime of x sub I. Okay, now after that you transpose this, or sorry, this is the result, right? So after that you multiply both sides by negative. So when you multiply this by negative, so this becomes negative x sub I. Okay, this becomes negative x sub I, and this becomes positive x sub I plus 1. Okay, this becomes positive x sub I plus 1. Then after that, then equal to, so this becomes negative, no? This becomes negative. So you transpose this to the other side, so retaining only this x sub I plus 1. So this is x sub I plus 1, so this becomes positive. When you transpose it to the other side, this becomes positive, and this one is minus because we multiply both sides by negative. So that's why you have here minus f of x sub I divided by f prime of x sub I. Okay, so that's how to derive it, class. All right, so here we multiply both sides by negative 1. Okay, so we multiply this by negative 1 and do the same on the other side. So multiply this by negative 1. So that's why it becomes negative. Okay, so that's the derivation. And take note that this f prime of x sub I, okay, we'll just erase this. So this f prime of x sub I, that is just the slope, right? So that's just the slope class. Okay, so going back to this graph, we have a definition that f prime of x sub n, so this is our x here is in terms of subscript n, this is our initial gaze. So f prime of x, so this is just the slope, right? Slope of the tangent line. So this is rise over run, or that is delta y divided by delta x, or equal to f sub x sub n minus 0 divided by same derivation class. This one x sub n minus x sub n plus 1. So again, this one is this point of tangency. If this is x sub n, then the height of this. So the height of this is what we call the this is what we call the f sub the value, that is f sub x sub n, okay, which is in our uh, normal derivation, so we call this height of the function as f sub f of x sub n. Okay, then delta y, our delta y, meaning this is actually our delta y. So this is our delta y. So this is our delta y, and this is our delta x, this one. So delta x is the distance from x sub n to x sub n plus 1. In other words, that is the difference, no? Because x sub n is just the distance from the y-axis. So this is our x sub n, and our x sub n plus 1, this is the distance from the same y-axis towards this. Okay, so to find this, the difference, delta x is just the difference, x sub n minus x sub n plus 1. This is our x sub n plus 1. So the difference, this is the difference class, which is what we call the delta x. Okay, why is it 0, minus 0? What does it mean? So the height, meaning we're considering 2 points class. So this point here, okay, so this point, so the height of this point is f sub x sub n. Then we have here the height at this point, okay, the height at this point, because we're considering, which is the height of this point is the same as the height at this point. So what is the height of this point? So this is just 0, right? So that's why we have here minus 0. Okay, so we have here the formula of our derivative. So from this, from this one class, we can rewrite this as x sub n plus 1 equal to x sub n minus f sub x sub n, because f sub x sub n minus 0, so that is the same as this. Okay, and this one we manipulated this, or we rearranged this in the manner that we did in the previous slides. So same, you from here, because you just make use of this equation class, just consider this. This is just an explanation, and this one you can eliminate the 0 because that is just 0, so you can make use of this. So in other words, you can equate f prime of x sub n equal to f of x sub n divided by x sub n minus minus x sub n plus 1. Okay, so the same process as what we did in the previous slides. So what you're going to do, you just cross multiply this one there, and this one cross multiply on the right side, and then multiply both sides by -1, then transpose this on the other side. So we will come up this formula. So this is the Newton's method plus Newton's method formula. Okay, we have here the algorithm for Newton's method. So step number one, first we need to evaluate the first derivative of the function, so symbolically. And then step number two, we use an initial guess of the root. We can call that guess as x sub I. I here means initial value or initial uh, as approximate value of the root of the function or the zeros of the function or the solution of the function. Okay, we call that x sub I. To estimate the new value of the root, initial and new value is given by this x sub I plus 1. So if initial if our initial say because our I here will range from 0 to any values, no? Our I is equal to uh, is an element uh, so anybody depends on the interval class now that you can see from the graph. So whatever is the value here, uh, you can have your I from 0 to uh, any number. Okay, uh, so this is given by this Newton's method formula. X sub I plus 1 equal to x sub I minus f prime, or sorry, f of x sub I divided by f prime of x sub I. All right. So step number three, you have to find the absolute relative approximate error. No? Absolute relative approximate error, and this is given by this formula. In this formula, epsilon subscript a, the absolute value of it, which is that's why we have the absolute relative approximate error. So approximate relative approximate error is just given by this formula x sub I plus 1 minus x sub I divided by x sub I plus 1 times 100%. All right, so that is the absolute relative approximate error. So that's step number three. And then step number four, we have to compare the absolute relative approximate error with a pre-specified error tolerance. So this will be given. So you have to compare your result from this specified error tolerance. And then use this flowchart. Is the absolute relative approximate error greater than the pre-specified error tolerance? If yes, then go to step 2 using new upper and lower guesses. And if no, then stop the algorithm. Okay? And you have to take note that you should also check whether the number of iterations is more than the maximum number of iterations allowed. If so, then you need to terminate the algorithm and notify the user about it. We have here some exercises, class. We'll begin with this, but the first one I will reserve this for your practice because this is one of the easiest problem. So here you're asked to find how many roots does the equation have, what are the intervals that contains the roots, and you need to solve for the roots using Newton's method with error of less than 0.0001. So this is the specified error class as mentioned in this slide. That is the pre-specified error tolerance. So this is the example of yes, specified error tolerance. Now we'll solve this. We'll show you the solution of this example for your reference when you solve that exercise class. So consider the problem of finding the positive number x with cosine x equal to x cubed. So same question, how many roots does the equation have? What are the intervals that contains the roots? And you have to solve for the roots using Newton's method with error of less than 0.0001. So sometimes class this error specified error tolerance is given in percentage. Okay, so when you convert this into percentage, so this will be 0.001%. All right, and then you need to graph the function showing your roots. Where are your roots located? Okay, so solving that problem. So consider the problem finding the positive number x with cosine x equal to x cubed. So first we can rephrase this given that as finding the zeros of f of x equal to cosine x minus x cubed. So this one class, we just let the function be equal to this one. So meaning you just transpose this to the other side. Okay, so transpose this to other side, so you have now the minus. Then you're combining these two and this one, so we can say that our function f of x equal to the difference of this. Okay, so this is our f of x. So we have f of x using the derivative of cosine, which is the negative of sine. So we got this result. So this is our f prime of x, the first derivative of the given function. And since cosine x is less than or equal to 1 for all x, now for all x, this cosine x is less than or equal to 1. So this is the value of cosine x. And x cube is greater than 1 for x greater than 1. So for example, is x, if x equal to 2, so 2 cube 8, so that is greater than 1. If x equal to 3, so 3 cubes, so 27, so greater than 1. All right, so x cube is greater than 1 for x greater than 1. So we know that our zeros lies between zeros and 1. Okay, so less than 1 or equal to 1, and this one is greater than 1, so you can say that the zeros, meaning the solution to the equation, lies in this interval 0 and 1. Right, we try starting value of x sub 0 equal to 0.5. We can try that one, but take note class, if you start with 0, this will lead to an undefined result. Now if you look at the Newton's method equation, it will give us undefined result, so do not start with 0. Okay, so here we start with 0.5. You can start with 0.8, start with 0.1. Avoid using 0 to avoid this undefined result. Okay, so this is the solution. So from the Newton's method formula, we have x sub I. Actually, we have the x sub n plus 1, right? We have x sub n plus 1 equal to x sub n minus f sub x sub n divided by f prime of x sub n. So this is our Newton's method formula in finding the root. Okay, so we have here our initial guess. So this is an initial guess. All right, so this is another way of presenting this one class. They're just the same. You also have another expression like x sub I plus 1 equal to x sub I. So don't be confused with this, they're just the same, minus f prime of x sub I, sorry, f sub x sub I divided by f prime of f sub x sub I. Okay, so they're just the same class. And now we have another one. Don't be confused, huh? So meaning here, if when I equal to 0, so when I equal to 0, meaning it's our initial giz. So when I is equal to 0, so this becomes I is 0, so this becomes x sub 0. So this becomes I is 0, so x sub 0. Okay, so from this formula, I is 0, so 0 plus 1, so that's why you have x sub 1. Alright, so this is also x sub I, where I is equal to 0, so you replace this with 0. And our initial giz when our x sub I, when I is equal to 0, so x sub I is equal to x sub 0. Okay, so x sub 0, where our x sub 0 is the first value of our estimate, no? First approximate value, which is we use, what did we use? 2.5, or sorry, this is 0.5. I think we use 0.5 here. So that's why we have here 0.5. Then substituting this, okay, and you get this result. And next we need to find x sub 2. We need to find x sub 2. So how to find x sub 2? So when I is equal to 1, so when I is equal to 1, so what will happen? Our formula will become, so if you use this formula, so when I is equal to 1, so we have now the formula becomes x sub 1 plus 1. So 1 plus 1 is equal to 2, right? So 1 plus 1 equal to x I is equal to 1, so this becomes x sub 1 minus this will be f sub x sub 1 divided by f prime of f prime of x sub 1. Okay, so what is x sub 1 plus 1? That is x sub 2. So we replace this with x sub 2 because 1 plus 1 is just equal to 2. Okay, so this becomes x sub 2. So this is now our formula to find x sub 2. Okay, so to find x sub 2, you need to substitute whatever is the value of x sub 1, where our x sub 1 is this one. So we have calculated x sub 1, which is this. So this is the value that you are going to substitute it here, and also here and here. Okay, then you get this result. So for x sub 2, you have x sub 1 equal to f sub x sub 1, and then you substitute from the given function. Okay, this one is the derivative, first derivative of the function. You substitute it, but this time you use another value. Instead of 0.5, you need to use this. Okay, and then you get x sub 2. And after that, to solve for x sub 3, so the same process, you can just repeat the process. So this is for x sub 3, that is just x sub 2. So this will be x sub 2. This is also x sub 2. This is also x sub 2. Okay, and then you substitute the values. So x sub 3 is equal to x sub 2. X sub 2 is equal to x sub 1, right? And then your x sub 3, is equal to x sub 2, minus f sub x sub 2 divided by f of x or sorry, f prime. This is f prime of x sub 2. Okay, so this is the formula class. That's why you have here uh, x sub 3. So you have this result. So you use this x sub 2. So this x sub 2 class is the value that you get from here, from this calculation, which is this one. Okay, so you substitute this value here in this equation, then you will get this, and so on and so forth. Then you get x sub 4, you get x sub 5, you get x sub 6. Okay, then if you look at the values, you have after the decimal you have 8, 6, 5, 4, 7. So more or less they becomes stabilized, no? For this value up to this 3. If you look at the next number, x sub 5, x sub 6. So if you look at this, so they are the same. And then the error that is being mentioned is, I think it already covers this. So this is the error here is the difference between this 1111 and 102. So the error is very, very less. So the error here is 0.000000 something. Okay, so you may stop your iteration. So in summary, this is the result class. Okay, so when you are going to substitute, no, when you are going to substitute this value to the root, so the result will be, because we're given the function cosine x equal to x cubed. So when you substitute that value class, either x5 or x sub 6, so this will holds true. They're almost very, very close to each other, almost equal to each other. So it means our x will be close to the true root of the given function. Okay, so I hope you were able to follow the explanation class. And we have here another example. I want you to also practice this. Okay, so same question class. How many roots does the equation have? What are the intervals that contains the roots? Solve the roots using the Newton's method. Error of less than 0.0000. There are 5 zeros. Okay, so that's all for today, for this video, and we'll continue the rest of this concept of Newton's method class, the drawbacks and the advantages of this in our next video. Thank you very much, and see you again in our next video. Bye.